Thanks very much. It's the first talk I've given where I'm being watched by a Dalek from the side of the stage. I was just hope the Dalek enjoys it. Yeah, I want to talk a bit about the invisible universe. So it's a big topic, the universe, very big, as Douglas Adams would have said. I work at Jodrell Bank, which is the big radio telescope about 20 miles south of here. It's part of the university here in Manchester, and there's a photograph of the telescope behind me here, the big radio telescope at Jodrell Bank, the Lovell telescope, looking up, very beautiful picture taken by our computer manager, Ant, looking at the North Celestial Pole. So you see in a long time exposure, you see the rotation of the Earth, you see the stars making this sort of cycle around the North Celestial Pole, the point on the sky directly above the North Pole. And I suppose before we start talking about the invisible universe, what we should talk about is the visible universe. What do we actually see? The visible window on the universe, what we can see out there in space. And I guess historically, people have been interested in the universe, in looking at the universe for many thousands of years. Here's Stonehenge, of course. The alignments of Stonehenge are well known. There's an alignment with the rising sun and the setting sun on the solstices is probably the primary alignment on Stonehenge. So the sky is very important to people at that time, maybe 5,000 years ago nearly. There's this beautiful structure here in Peru called Chanquillo, which is an amazing thing. It's a hillside. I don't know if you can tell the scale from that photograph. That's a landscape photograph. And there's a hillside where these notches have been gouged out along the ridge line of the hill so that you can stand on certain points. And if you're looking east, you can stand and see the sun rising between these notches at different times during the year. Stand on the other side, you get to see the sun setting, of course, through the same notches. So it's a calendrical device that was constructed there back about 300 or 400 BC. And if you haven't seen this before, this is an amazing mechanism as well. It was found on a shipwreck that was found in 1900 off the Greek island of Antikythera. And this is called the Antikythera Mechanism. This is part of it, a system of cogs and gears that our best understanding is that it was used to predict astronomical events like eclipses, for example, or other types of movements in the calendar. So a very early computer, a mechanical computer there, all about what happens in the sky. So clearly we've sort of had this impression of being interested in what the sky means. We've made up stories about what there is in the sky. We see with our eyes, we see the stars and the planets. And you might think I've misspelt planets there, but I've not. I've deliberately used the original term, so I think it's probably Greek, planetes. It means wanderer. So things that look like a star to the eye, so a bright point of light, but they move in a different way than the stars. So for example, you would go out at night and you would see a pattern of stars, the constellations, you'd see the same night after night. And one time of the year, you'll see the stars that are in the opposite direction to the sun on one side of the sun. 6 months later, you'll see the star patterns that are in the other direction at night. Those patterns stay fixed, but wandering about on those patterns, you see these things called the wanderers, the planets. In early times, nobody knew why they wandered. We now know they actually are orbiting the sun, of course, and that's why they move against a distant background of stars. I don't know whether we can bring the lights down on the picture. I have some dark, there we go, it's a bit better. So here's one of my own lovely photographs of the sky, taken on holiday a few years ago in Scotland, where the sky's a bit darker than it is in Manchester. But you see a sky full of stars. And of course, we know stars are powered by nuclear fusion, and the hot surfaces of stars are radiating light in the visible light of the spectrum, and that's what we can see there. Here's another one of my holiday photographs. I'd like to show you my holiday snaps. So this is actually, I was working, believe it or not, in South Africa at the Astronomical Observatory down in South Africa, just sort of inland from Cape Town. And there again, the sky is very dark. But one of the advantages you get from the southern hemisphere is that you get to see the middle of our Milky Way. So this patch of this sort of band of light that's running across the middle, threaded by these dark regions, which are basically the dust clouds between the stars, blocking your view of the distant stars. That's very obvious in the southern hemisphere. The center of our Milky Way is basically in the middle of this region here. Who's seen the Milky Way, by the way? Okay, so a higher than average proportion of people, so that's good crowd. But it's hard to see the Milky Way, of course, with light pollution. You can see it from this country. Get away from the street lights, you'll see the Milky Way as a band of light running across the sky. Quite hard to see these dust cloud patterns in the Milky Way here. They're much more obvious in the southern sky. So here's a photograph. It's taken from a website called chromoscope.net, which if you haven't looked at is well worth a look. It's called, this is the visible sky. So this is the whole of the visible sky all the way around us. So if you can imagine looking at the Earth, then we know that the Earth is a sphere. Who thinks the Earth isn't a sphere? Some people could have put their hands up because it's not actually a sphere, it's an oblate sphere, it's a bit flattened, right? But okay, we haven't got any flat earthers in. No, okay, good. So if you sort of imagine the Earth as this roughly spherical thing, and you make an atlas and you sort of unpeel the surface of the Earth and lay it flat, then this is the same thing as has been done here with the visible sky. So the sky around us is basically a sphere. It's the celestial sphere. As we look all around us, we can take a picture of that whole sphere and then unpeel it and lay it flat in this way. And what you see in this picture is our Milky Way. It's the galaxy, the group of stars that we are part of, that runs basically across the middle in this particular representation. It's the horizontal feature right across the middle of this picture. And you see these dust clouds again between the stars that block our view of the more distant stars. So you could ask why, probably bring the lights back up a little bit if you need to. You could ask why is the Milky Way like this? And this is my model of the Milky Way. This is made with a cake board and two bun cases. Glued on either end on either side of the cake board. So when you see it from the side here, what you see is a sort of flattened disk of stars. When you see it from directly above, you see this roughly circular disk. That disk has spiral arms in it, and we're sort of 2/3 of the way out from the middle in one of the minor spiral arms. But when you see it from the side, when you see it even from where we are, we look out at the sky in all directions, but we'll see the stars distributed mainly in this sort of band that runs across the sky because they are in this flattened disk. So those are the sorts of things you can see with your eyes. Of course, 400 years ago or so, we started to use telescopes. So we augmented our eyes in that sense. We started to use, this is Galileo, who put together some lenses in a tube, and that allows you to actually zoom in on things. It magnifies your view, but it also gathers more light, so it increases the size of your effective size of your pupil to be in the size of the lens, or if you're using a mirror in your telescope, the mirror on your telescope. So you can see fainter things if you've got a bigger collecting aperture. Of course, this is a lovely picture of Galileo's notebook from January of 1610, where he used his telescope to look at Jupiter, so one of these planets. And you see these little pictures of Jupiter in the middle here, and then on either side of them, these little asterisks that represent the four largest satellites of Jupiter, the four largest moons of Jupiter, the Galilean satellites, which he was the first to see, because you needed that extra light-gathering power and that magnification to see that they were there, and also to see that they revolved around Jupiter, so contributing to the realization that the Earth was not at the center of the universe, and that things could orbit something else rather than, say, orbit the Earth or even just orbit the Sun. So I'm going to go back to my picture. Can we take the lights down again? Sorry, I know I'm messing you about a little bit. Yeah, okay. So for those of you nearer the front, you might be able to see, you see loads of stars. These are all stars, basically all in our Milky Way, in our galaxy, that you can see are individual stars, and many fainter ones that are very, very hard to see. But sitting up here, if I can indicate a point on the slide here, there's actually a fuzzy-looking star. So this fuzzy-looking thing here, it does look different than the other stars. That fuzzy-looking thing is not a star, it's another galaxy, an entirely separate group of stars. So in our Milky Way, we have maybe several 100,000 million stars, several 100 billion stars. That is another group of stars in a completely separate galaxy. It's the Andromeda Galaxy. Probably bring the lights back up again now, if you like. Just to keep you on your toes. So this is what you see through a telescope looking at the Andromeda Galaxy. So if you've got good eyesight, you've got dark skies, you can see the very central part of the Andromeda Galaxy, the bulge, the bun cases on my model. The sort of group of stars near the center is the brightest part. That bit is actually visible to the unaided eye, if you know exactly where to look in a dark sky, just about. But this whole extensive disk of stars and gas and dust, you really need a telescope to gather more light and produce these beautiful pictures. So this looks like my model, seen at a sort of angle to a disk, seen at an angle to the line of sight, and pretty much like our own Milky Way, we think. Okay, just to remind us how big the universe is, and I mentioned it was a big. Is that me? I mentioned it was a big universe, very big universe, as Douglas Adams had it. Here's the sun. That is actually another holiday photograph. I shouldn't go on. That's the Warren Bungles in Australia. There's a lovely telescope called at the Anglo-Australian Observatory there, inland from Sydney. But looking at the sun over there, the light from the sun takes about 8 minutes to reach us. Traveling at the speed of light at 300,000 kilometers a second. And of course, if that same light went on past the Earth and traveled off out into space, you know, we're quite happy to sit here, I hope, for at least 8 minutes, waiting for the light that's just setting off from the sun to get here. But we're probably not happy to sit here and wait for that light to get to the nearest other star, because we'll be sitting in the room listening to my talk for the next 4.2 years. So it sort of gives you a feel, that sort of scale gives you a feel for the size of the universe. So the Andromeda Galaxy that we just saw there, that you can see the central part of with the unaided eye, is actually about 2.5 million light years away. So the light that we see from those stars has taken 2.5 million years to reach us, traveling at 300,000 kilometers a second. And if this were our galaxy, we would be located where that little yellow dot is there. And the size of that yellow dot has been carefully chosen so that if the sun were at the middle of it, the light that set off from the center of the dot and took 8 minutes to reach us from the sun to the Earth, and then 4 years to reach the nearest other star, would take about 1,000 years to reach the edge of the yellow dot. And so across the whole galaxy, light takes about 100,000 years to cross it. So galaxies themselves, individual galaxies, are huge structures. And I think the important thing about astronomy then is when we use one of these telescopes to see the universe, then we effectively have a time machine, because we see back in time. We see the universe as it was in the past. And that's very handy, because it means we can sort of get some idea as to how the universe has evolved over time. We don't get to see any individual bit of the universe evolve over time, but we see snapshots of the universe as it was at larger and larger distances from us, because those are points farther and farther away in time in the past from us. Telescopes have obviously evolved over time since Galileo. This is one of our largest telescopes. Does anybody know what the VLT is? A very knowledgeable audience. The very large telescope, and this is look, this is me. I'm still a relatively young spring chicken. I can bounce just about. But this is me. Beardless, you can't really tell. Thank goodness it's quite pixelated, this picture. But this is me trying to illustrate the size of the telescope rather than the size of the universe. It's actually 8 meters in diameter, that telescope. So if you think about your eye, and you think about how your pupil gathering light, then with one of these pieces of technology, you're gathering far more light, because the pupil is the size of the mirror. So the size of the mirror is, if I start at the side here, I don't know, let's start here. And I go 1, 2, 3, 4, 5, 6, 7, 8. The mirror is 8 meters in diameter. So imagine a circular aperture that size, how much more light it collects than your pupil. It therefore allows you to see much fainter things than your eye alone could see. And that's basically the power of these big telescopes. Now, that's the sort of visible universe. It's clearly very useful to have these telescopes to see the visible universe with visible light. What about the invisible universe? Well, here's, again, I'll plug Anthony's picture at Jodrell Bank. This is the lovely Mark II telescope at Jodrell Bank. Doesn't get the attention it deserves, this telescope, so we should all give it some love. It's a lovely telescope, the Mark II. It's smaller than the Lovell telescope, which is the big famous one, but a beautiful thing in itself. If the Lovell telescope wasn't there, everyone would be fawning all over it, saying how lovely it was. But here it is with a lovely rainbow around it. And of course, the rainbow is the rainbow of visible light. But beyond that sort of visible rainbow, we have effectively an invisible rainbow. So we have all the other forms of electromagnetic radiation. Beyond the red, we have infrared. Beyond that, we have microwaves, we have radio waves. Out beyond the violet, ultraviolet, X-rays and gamma rays. And so there's this whole sort of other area of exploration that we can use to study the universe. So if I remind us with, perhaps sorry, take the lights down again. This is the visible sky. So we saw that before with the light from stars largely, and the light blocked by the dust clouds between the stars. But if we now look at the same picture of the whole sky, but as seen by radio telescopes, this is what we see. Okay, now one thing we should say about this is the color is not a real color. So radio waves don't have color in the sense that we have reds and blues and greens and so on. So in fact, the representation is this is just a color scale where it ranges from black is the faintest to white is the brightest, and it goes through a range of shades of this sort of pinky color. So that just represents brightness in the radio part of the spectrum. So you can effectively point a radio telescope anywhere on the sky, and you might just have a dial at the back end of it, or a chart recorder or something, and it would measure the strength of the signal from that direction. And what was done with this map was to move the telescope around the sky and just see how the brightness changed as you change the pointing position of the telescope, and then plot that out on a picture like this. And in fact, to see the whole sky as this is, requires you to have telescopes in both the northern hemisphere and the southern hemisphere. Of course, the Earth, this lovely globe-shaped thing, spins around. If we're up in the northern hemisphere, we really only get to see the bit of the universe that's above the Earth. If we're down in the southern hemisphere, we get to see the bit that's below us. So this is combined data from the Lovell telescope at Jodrell, the Effelsberg telescope in Germany, and the Parkes telescope in Australia. And what do we see in this picture? You see the Milky Way, right? Go back to the visible sky. The Milky Way is this horizontal band across the middle with the dust clouds between the stars blocking your view. There's a horizontal band across the middle in the radio spectrum as well. But what you're not seeing in that picture is you're not seeing stars. It's not stars that are producing the radio waves in this case, it's the stuff between the stars. So in this case, it's the electrons spiraling around the magnetic field of the galaxy that are producing the light. We also see some very bright sources that are not at all obvious in the visible part of the spectrum. So you see something bright at the middle of the Milky Way. In fact, in the visible light, our view of the middle of the Milky Way is pretty much blocked by the dust clouds between the stars, between us and the center of the Milky Way. But there's clearly something there very obvious in the radio picture. Over here, there's a couple of very obvious bright things in the northern sky. One's in the constellation of Cygnus, the other in the constellation of Cassiopeia. If you went back to the visible light sky, really there's nothing noticeable there at all. You would never even think there was something important there. So until we looked at the sky with radio telescopes, we had an extremely limited view of the universe. We're going to learn different things about the sky by looking at different wavelengths. And I just want to put this picture up because it illustrates why stars are not obvious in that radio picture. This is a spectrum called a Blackbody Spectrum, which is basically the light that you get from opaque objects, so warm, hot, opaque objects. The light that's being produced has this characteristic rise and fall. Where the peak at which where the peak occurs, the wavelength in the spectrum where the peak occurs is determined by the temperature. So the hotter the object, the shorter the wavelength of the peak of this radiation. So it's the same reason why it's, if you took a lump of metal, or maybe you've got a traditional cooker with a ring on it, that you warm it up and that ring initially isn't glowing, but as you warm it up, it starts to glow a sort of dull red color. That's the blackbody radiation from that lump of metal that's warming up. Similarly, if I had an infrared camera now and I looked at you guys, you would all be glowing brightly, shining with your own light being produced by your warm bodies that show the infrared, in this case, that's being produced by the temperature your body is at. The blackbody spectrum peaks in the infrared part of the spectrum. So a night vision camera is designed to pick up the infrared, and we glow because we are at a reasonably warm temperature that's bright in the infrared. Stars are at temperatures, the surface of the sun is at a temperature of about 6,000 degrees. But that means that on a picture like this, then a 6,000 degree thing is actually this line running in here, and its spectrum, its blackbody spectrum, peaks somewhere in the visible part of the spectrum. So the sun produces most of its light in the visible part of the spectrum because of its surface temperature, which produces a blackbody spectrum like this. And that's obviously why we've evolved to have eyes that look at visible light, because that's what the sun's producing all around us. That's where most of its energy comes out. But if you follow the blackbody curve to longer wavelengths, so we're heading out into the infrared and then eventually into the radio, you see how this thing falls off. By the time you get to the radio, stars are producing very little light at all by this mechanism. So you don't expect to see, in that case, the stars very obviously in your radio picture of the sky. But what you do see is a load of other ways we can produce light, a load of other ways we can produce electromagnetic radiation. And I'm not going to go into all these things, but there are other thermal mechanisms to do with temperature, but also other non-thermal things. So when I said electrons spiraling around the magnetic field of the galaxy, that's a mechanism called synchrotron, where particles moving at a high fraction of the speed of light are spiraling around the magnetic field, and that generates radiation as you move about a charged particle. As you wiggle this charged particle about, you accelerate it, and it produces these radio waves that we see. That's what dominated that last picture. So here's another, just to give you an example. Those two bright objects that I showed you before that were over to the left-hand side of my picture, I've just sort of zoomed in on that bit, the constellation of Cygnus and Cassiopeia. Here's the radio picture. The top is the visible picture, and below it is the radio picture. And you see how dramatic these sources are. They really are some of the brightest things in the radio sky. They were discovered almost as soon as we started using radio telescopes back in the 1940s. And they were called radio stars because they looked a bit like stars in the visible light sky, and we really had no idea what they were. If I pick Cygnus A, so this is this thing here, and we zoom in with a really big telescope, and we collect as much light as we can see, and we zoom in on a patch of sky around it, that is what we see. So this is a visible light view, and what you see here is lots of bright points of light, which are stars in our own galaxy. So we're looking out through our own galaxy, so we see in the field of view, we see stars in our own galaxy. But then there's the fuzzy thing in the middle. Looks a bit like that Andromeda Galaxy I said right at the beginning, that you can see this little fuzzy thing in the sky. So that's actually a distant galaxy, quite a relatively faint, distant galaxy, and the fuzzy thing is the light from the stars in the disk of that galaxy. If you zoom in now with a radio telescope, and in this case, to zoom in with a radio telescope, what we do is we connect lots of radio telescopes together across large distances, and we combine them together to make a sharp image, a sort of zoomed in sharp image. What we see is this. So the two pictures at the top are on the same scale. It's just that one of them is the visible sky, and the other one is the radio sky. And of course, what's remarkable is that the stars visible on the left and not there at all on the right. If the fuzzy thing in the middle isn't there, except there's a bright point of radio light right at the center, or a very tiny bright point of radio light. And then perhaps the most obvious thing, these two big, bright lobes of radio emission, we call them, to either side. And you can see connecting the point in the middle out to one of these bright lobes, and there's a little bit of an indication of a similar thing pointing to the left-hand side one, but out to the right-hand side there you see this very thin structure. We call it a jet. So what we now understand these objects to be is they are distant galaxies. They're powered by the supermassive black hole that's at the center of that galaxy. So where you see the bright spot in the middle, what you're seeing is radio emission from the region around that supermassive black hole, perhaps billions of times the mass of the sun. And shooting out from the region around it are these two oppositely directed jets, moving at very high fractions of the speed of light. And where those jets smash into the medium around the galaxy, the intergalactic medium, then you get this sort of splash effect as they're ramming into this stuff. Lots of energy, lots of kinetic energy is being converted into other forms of energy, and a large part of it into the radio emission that we see here. So in the visible sky, what you see are stars powered by nuclear fusion. In the radio sky, what you see are these, what we originally called radio stars. You see them scattered all over the sky. They're in fact galaxies powered by gravity, powered by the gravitational accretion of material onto supermassive black holes. So a completely different phenomenon that we would never have seen unless we'd looked at the invisible universe. Now, I'm always a little bit loath to do this, but then I just do it anyway. To turn the signal from our radio telescope into a sound. And the reason I'm a little bit loath to do it is because if you're not careful, it promotes the myth that radio astronomers listen to the signals from the radio telescope. And I guess it's because we listen to the radio. We listen to the car radio or something, and so you think, oh, radio telescope, we are listening to the universe. And you will, I'll sort of allow it occasionally to be said, but it's not true. We don't listen to signals. We're picking up electromagnetic waves. They're the same physical phenomenon as visible light, but just at longer wavelengths. So it's not a sound we're picking up. You can turn it into a sound like you can turn virtually anything into a sound. It's just some data. In this case, we pick up voltages at our receivers. You can put those across a speaker cone. You can make the speaker cone vibrate in and out just in sympathy to the strength of the radio signal that's coming in. And if you do that, this is what you hear. Might explain why we don't spend our time listening to those signals, I guess. But in general, they're just noise. It just sounds like noise. It's just a hiss. Obviously, radio astronomers could listen to that sort of thing all day. But that is actually, within that, there is some information. So the strength of that noise would be a parameter. You could look at the strength as a function of the wavelength in the radio spectrum. That would be another bit of information you could get from that. That was actually the other bright source in that picture that I showed you a minute ago, which is a star that exploded in our galaxy back in the year 1670. It's called Cassiopeia A. But it produces these radio waves. They just sound like hiss. I can't resist playing you these sounds because these are so different that they're quite fun. So these are, if you point your telescope in a random direction, you'll get the hiss. If you point your telescope in a very specific direction, there are these things called pulsars, which make rather different sounds when you convert the radio signal into a sound. This is called the Vela pulsar. This is just repeating now. It's basically it's a flash, but it's a flash that happens 11 times a second. So it's 11 times a second, if you can imagine that. And it sort of changed in brightness, so you had this sort of interesting syncopation effect. There's another one of these things in the middle of a supernova remnant, the explosion of a star. It's called the Crab Nebula. So the Crab pulsar sounds like this. So that's now spinning 30 times a second. Sorry, that's now flashing 30 times a second. Flash, 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 flash. And it starts to sound like a road drill. And some of these things flash even faster. This last one flashes 642 times a second. So you're starting to get a picture for how this might go. And I'll just stop that there, because it's a bit painful. That's one of the fastest flashing pulsars there are. These things actually, when they were first discovered, they were so weird. Jocelyn Bell discovered them in Cambridge 50 years ago this year in 1967. And when they found them, they thought these regular sounds were unusual. They normally have got that hiss, this regular flashing. So they called the first one LGM1, Little Green Man 1. Because there was this sort of idea, maybe this is a deliberate signal, maybe this is a semaphore type thing, a deliberate flashing. We now know that it's actually something spinning. So it's a very massive object, about 1.5 times the mass of the sun, but collapsed down to be about the size of a city, so about the size of Greater Manchester, about 20 kilometers across. And they produce these radio waves from the magnetic poles. And so as the star spins, these waves sweep around the sky in a beam that you see a flash from every time it comes past. So you get this very regular flash that's just the spin of the neutron star, it's called, this underlying massive object. So very much like a lighthouse effect. And you see that flashing. So they're amazing things for understanding fundamental physics. And just as another example, just one more example of what we see in the radio spectrum with radio telescopes, this is the fading glow of the Big Bang. It's called the cosmic microwave background. This is the best ever picture that we've made of the cosmic microwave background. It was made by a spacecraft called Planck, the Planck spacecraft named after the physicist, which was launched in 2009, and it spent several years spinning around, sent to a point four times farther away than the moon in the opposite direction to the sun, called the Lagrangian point, L2. And it sat there, it span around, mapping, gradually building up this map of the whole sky. And in this picture, what you're seeing is basically the brightness of the microwave radio sky at quite fine resolution, quite a sharp view across the whole sky again. So this is like a map of, an atlas of the Earth where we traditionally have the Americas on the left and Australasia down on the bottom right somewhere. So this is a map of the whole spherical celestial sphere laid flat. And the colours are representing brightness, so that you've got warmer and cooler regions with the reds and the blues, and that's effectively the intensity of this, what turns out to be a very almost perfect black body. So that same shape that I showed you before, this rise and fall. So it's basically light that's set off about 380,000 years after the Big Bang. It's been traveling in all directions through the universe since, and as we look out into space, we see this light arriving from a distant region. It's taken almost 14 billion years to reach us. It's arriving now from a point in space a long way away, 40-odd billion light years away now, because the universe has been expanding ever since it set off. But by mapping it, we see the structure in the universe as it was 380,000 years after the Big Bang. So it's the sort of farthest back, really, in time that we can see with our telescopes. An amazing photograph. And of course, this structure, these little lumps and bumps that you see in here, those structures are the structures that would have grown under gravity to form the galaxies of the stars and eventually ourselves. So these days, we use telescopes right the way across the spectrum. So all the way from gamma rays at one end to radio waves at the other. And the bit at the top here, the picture at the top shows you the atmospheric transparency. So it shows you where the light, the electromagnetic waves can get through the atmosphere to reach the ground. And the two main regions of the spectrum where that happens is in the visible spectrum. So in the middle there, there's what we might call an optical window, a window on the universe. And on the right-hand side, there's the radio window where the radio waves get through to the ground as well. And at other wavelengths, you either have to get up on top of a mountain to get above most of, say, the water vapor in the atmosphere, to look at these little bands in the infrared here, or even fly a telescope on a spacecraft, on a satellite. So when you're talking about gamma rays and X-rays, you're typically talking about an ultraviolet. You're typically talking about space-based observatories, which clearly were not possible until 60 years ago, a few weeks ago, when we launched Sputnik 1 and had the first satellites. But now, an astronomer would use as much of this as we can to try and understand what's going on and piece, get different information from each bit to piece it together. That's electromagnetic radiation. That's where we get most of our information from. But there is what we might call a particle window on the universe. So rather than electromagnetic waves, radio waves, X-rays, gamma rays arriving from distant space, there are actually particles that arrive from space. Sometimes they have negative impacts, shall we say. This is a meteor crater in Arizona. So if a big lump of stuff gets all the way through to the ground, it can be a problem. But it actually brings material that tells us something about space. And even in some of these materials, you can find the evidence of nuclear processes in stars that have generated the material that our solar system is made of, and then you can bring it down to Earth for us to study. There are other particles, of course. I mean, this is a brilliant observatory, amazing thing. It doesn't look much like a telescope. The telescope itself is buried under the ice at the South Pole. It's called Ice Cube for obvious reasons. It's a sort of cube buried under the ice, so it's nothing to do with Alien versus Predator or anything. But it is the same sort of thing, a buried structure that actually is designed to pick up neutrinos. So neutrinos, elementary particles that are flying through us all the time, coming from, for instance, from the center of the sun. And you need a large volume of detectors to detect them, and you need to distinguish them from other sources of interference. So burying it under the ice was a good idea in this case. And that observatory is buried underneath there, looking at particles coming from space. And actually, in this case, can tell us something fundamental about what's happening right in the middle of the sun, which otherwise we would obviously find it very hard to see. Another window on the universe beyond visible light, the invisible light, the particles, and this is, of course, a very important area now, is the gravitational window on the universe. And the first example I want to just mention is dark matter. Dark matter is, if I go back to my model, here's my model of a galaxy. Galaxy disks rotate, so they spin. And we can measure the speed at which these galaxy disks are spinning because we can look at, for example, we can look at hydrogen, emission from hydrogen in the radio part of the spectrum that we know should produce radiation at a very particular wavelength in the radio spectrum. And we can look at whether that's Doppler shifted, so we can look at whether it's shifted to the red or to the blue by the motion of the galaxy towards or away from us. So you can map the speed at which things are spinning by looking at these sorts of lines, these astrophysical lines that are produced at particular points in the spectrum. And it was, most of the work on these galaxy disks was done by an astronomer called Vera Rubin back in the 1970s and 80s. And she sort of measured the spin of these galaxies, measured the speed at which they were spinning. And just as in the case of the planets orbiting the sun, the speed at which the planets move is determined by the gravitational force between the planet and the sun. The more mass there is, in the case of the planets, the more mass in the sun, the faster they would spin. And so in this case, when you measure the speed at which these hydrogen clouds are rotating in this galactic disk, you can try and weigh the galaxy, first by measuring the speed at which it's spinning, and second by adding up all the stuff you can see. So you can add up the masses of all the stars and all the gas clouds that are producing the radiation at all the various wavelengths you can detect, and you make an estimate of the mass of the galaxy that way, and the two didn't agree. So basically, it turns out there seemed to be far more gravitational mass in these galaxies than there was visible mass. So there was stuff there that was not producing light, and it therefore became known as dark matter. And it turned out, you can study that in lots of other ways as well, but it turns out that dark matter, there appears to be about 5 times more dark matter than what you might call normal matter, the stuff that we can see the electromagnetic radiation from. And we don't know what dark matter is, right? It's a problem. We still don't know what dark matter is. It does appear to be there. The other gravitational window we've got is a new one. It's gravitational waves. And a gravitational wave is a ripple in space-time predicted by Einstein by basically moving masses around. So if you have a massive object here, it's gravity. Einstein's understanding of gravity was a geometrical interpretation of space-time where the mass curves space. And then, the curved space is what we then interpret as the force that draws us in towards that massive object. If you sort of jiggle that massive object around, then you can imagine these ripples traveling out in this curvature of space-time. And those ripples, we think, are spreading through the universe. We know are spreading through the universe. We've known they existed since the 1970s when we observed their effects in a pulsar system, those flashing objects that we heard earlier. But they were directly detected very, very recently in the last year or so. And their effect is something like this. So if this is us standing here in the room, if a gravitational wave comes past us, what it does is it stretches us and squashes us. So basically it stretches us, and then it squashes us. And then it stretches us again, right? So it stretches and squashes. So I don't know whether we've got the lights, actually. Should we try it? It's a bit of exercise. Should we have a go? Let's do a gravitational wave. Who wants to do a... We just stretch and squash. Oh, very good. Somebody's staying stretched. So we're going to do a gravitational wave. Yeah, a gravitational Mexican wave, as they're sometimes known. Right, so we'll start with me. And then when I do it, the first row have to do it. Once the first row's done it, the second row can do it. But wait until the ones have done it in front of you. And again, and again. Let's see if we can get one going. Right, ready? Stretch. That's not bad. There were a few people. Oh, it's coming back again. It's bounced off the back wall. So gravitational waves stretching and squashing us all the time, stretching and squashing us. Now, this is a total exaggeration, right? And the reason why is because of this formula. This is the formula for what's called the strain of a gravitational wave. So, I'll tell you what the terms are in this formula. So delta L over L is the fractional change in length. So if the length of something is L, delta L is the change in length. So delta L over L, the fractional change in length. So I suppose if that was us, if I was 2 meters tall, which I'm not, then, if I sort of, stretched myself by 20%, then this number would be 0.2 or something, I guess, right? And then over here, we've got the size of a black hole. GM over C squared is basically the sort of size scale of a black hole. So mass of the black hole, G is the gravitational constant, C is the speed of light. And then you've got the distance, because actually the strength of these gravitational waves falls off with distance, as you might imagine. So the strain goes down as 1 over d. And then the speed the black holes are moving. So in this case, what we're imagining is 2 black holes going around each other. So you should have asked, if I got a big black hole, big massive object, some of these black holes can be 10, 20 times the mass of the sun, and I jiggled it, it would produce this wave like we just simulated going out through the universe, right? The question is, how do you jiggle it? You don't have a sort of God's hand comes and gets hold of it and jiggles it. So the way of jiggling it is to have 2 of them orbiting one another, and then there's this sort of natural jiggle that's happening that's producing these waves. So there's your equation, and you could dump in all your numbers, and actually, as an exercise for the reader, I'm sure you can all remember this formula, you can go away and work out, okay, what's that? You could work out how far away you'd have to be from a black hole that weighed, say, 10 times as much as the sun for the strain to be something detectable in the stretching of your body, right? So I'm not going to do it now, but you can work that number out, and you might be interested to see how close you'd have to be to a black hole for a gravitational wave to be detectable. Because the ones that we are detecting now, the strain is 10 to the minus 21. So the fractional change in size is 10 to the minus 21. So it's not 0.2, 20% change in somebody's height or something. It's a very tiny number indeed. But we are able to detect it amazingly with the LIGO Observatory, which is in Livingston in the US, which is basically two arms of an interferometer with a laser bouncing backwards and forwards. It measures the length of these arms, and it measures them to some outrageous precision. So this is a hydrogen atom with an electron nominally spinning around the proton. Zoom into the proton, and this is the size of the proton on this scale. This is the edge of a proton, and the amount by which they're measuring the change in length is that. 4 times 10 to the minus 18 meters is the change in length of one of these arms of this interferometer. It's absolutely phenomenal, amazing technology, but it works. And there are a number of these observatories around the globe now, 2 LIGOs and others like Virgo, and there's a LIGO in India on the way. And this is the sort of thing that they're detecting, are these ripples in space-time from these merging black holes. 2 black holes, as they spiral around one another, they radiate away energy in the form of this gravitational wave radiation that we can detect. And as they finally spiral in, as they lose energy, they spiral together, and then they collide, they merge together, and you get a sort of burst of gravitational waves that you can see on this picture at the bottom here, as the things come together. So this is the curvature of space-time that's represented in the picture. So it all speeds up as these things come together, and then this thing slows down the movie just so you can see what's happening as these 2 things start to merge together. And it's just a sort of fraction of a second in the end. So you can actually turn that into a sound. If we just play that in the same way we can turn radio signals into sound, you can turn gravitational wave signals into a sound, and this is the chirp that you get. which is 2 massive black holes colliding. You'd have thought someone would have made that sound more impressive. I don't know. Anyway, there we go. There's now been a number of these detected, and there will be more of these things being detected now that the technology is there. And you've basically got these systems of different masses coming together to make larger objects and probing a whole new area of parameter space. So, windows on the universe. We have visible light. We now have invisible light, radio to gamma ray. We have particles, things that actually arrive from space, and we have gravitational waves. But there is a problem. We shouldn't finish saying we're amazing. The problem is that this dark matter problem, 5 times more dark matter than ordinary matter, if you like. We still don't know what dark matter is. And then there's this other big elephant in the room, which is dark energy, which in fact dominates in terms of the energy density of the universe, something that's causing the universe to expand faster and faster rather than it being pulled back together. And I'll just finish with Donald Rumsfeld's wisdom, because I think it's true, which is that there are things we know, and there are things we know we don't know. And here's some of them. We didn't know about dark energy until 1998. The first evidence for dark energy came about then, but now it's a massive big problem for us. And then there are things we don't even know we don't know. And I think that's one of the things that for me makes this subject interesting. Thanks very much.